All right, today we're going to talk about inverse functions and rational functions. First, we're going to review some of the models we've looked at so far. The first one would be a straight line, and in this case it goes through 0. We call that direct variation, and we notate it with y equals ax. And that means if x goes up, y goes up. Time studying, you put more time studying in, you get higher grades. Simple stuff. Ooh, famous double lines. The other types we have tried are parabolic, which looks like this. And that was a y equals ax squared. And I know both the direct variation had a plus b on it, but we're not going to use those for this purpose. This had a plus bx plus c, but we're not going to use those for this purposes. And we also did swoosh, the square root function, y equals, we'll put an a out front, square root of x. So now we've got inverse variation. What is an inverse variation? Well, an inverse variation is something that has the opposite effect. So we put the x on the bottom. So if x goes up, y actually goes down since they're on opposite sides of the fraction. Example of this would be price. The price of lunch goes up at Carmel, then the demand goes down. Less people would want to buy it. What does it look like? Well, we'll get into the graphing a little bit more later. It's got a very different graph, and if you want to make a t-chart, go right ahead, but I prefer just to put it in a calculator to see what it looks like. It does this. This is called an hyperbola, or hyperbola to the less intelligent of us, and it is always in pairs. So there's a branch up here and a branch on the bottom. And notice the arrows just keep going on and on and on. They actually get closer and closer without ever touching the x-axis, and we call the x and the y-axis asymptotes. And they are what I just said. The curve gets closer and closer, but never actually touches them. If you can imagine walking towards a wall, and I say, keep getting halfway closer, halfway closer, halfway closer, you'd never actually touch the wall. You'd keep just getting closer and closer. That's what an asymptote is. It's a wall that the line never touches. So, some problems. How do we determine if it's inverse? Well, this one's easy. That's actually the definition. If we take x and divide it out, get y equals 4 over x. That is definitely inverse. This one, we get rid of the 2 by moving it over. Get y equals 2x. That is direct. And a common misconception, people look at this and say, oh, this must be direct. But it's not, because it's not y equals ax. It's got an intercept out here. So that is not considered direct variation. We can get into all that detail another time, but for now, just remember, if it has a y-intercept, it's not direct. It's got to go through 0, 0. So, showed you the graph before. We'll do 2 of them. And as in the previous units, you do not need to be precise. It's just going to run up closer and closer and never actually hit the x or the y-axis. For this is y equals 1 over x. For y equals 1, negative 1 over x, if you remember, the negative flips it across the x-axis. So the one that was up here has now been flipped to down here. And the one that was here has now been flipped up here. Negative does not pop up that much, but you should remember the rules for graphing in general. moving to the next part of our note sheet. So how do we graph them? I'm going to dot in the parent graph, as we've done before. The parent graph looks like this. And for y equals 2 over x, it gets further away from the origin. So y equals 2 over x moves further away. Stays in the same quadrants, doesn't shift up, doesn't shift down, just moves further away. Again, we'll dot in the parent function. This is y equals 1/2 x. And now instead of getting further from the origin, it gets closer. This is y equals 1 over x plus 1. And it's inside the function now, so we know it goes left and right. So the plus 1 we think should move to the right. Instead it moves the asymptote 1 over, which will be x equals -1. And now we just draw it in normally. For the last one, y equals 1 over x plus 3. We have the 3 is outside the function, so we know it's going to move it up and down. So we go 1, 2, 3 up. And again, we just draw it normally. And that's the basics of graphing. We'll get a lot of practice on those. I'll leave that for a moment, not go too fast. So if I gave you something and I said that these two variables, y and x, are inversely related, how would you write the equation? How would you find the a value? So you have y equals a over x. Well, it's actually very simple. We have a y value, we have an x value, just plug them in, solve for a. 6 equals a over -3. Multiply both sides by -3. These cancel. We get a equals -18. You can check that if you want. Y equals -18 over x. When I put in -3, I get out 6. It checks. It's a very simple problem to do. Just make sure you find that it says they are inversely related. And finally, if we have a data set and we're told this may or may not represent an inverse variation, how do we determine if it does? And earlier we said y equals a over x can be written as xy equals a. So we should have that xy always equals a constant. So we multiply them. -5 times 2.4 equals 12. -3 times 4 equals 12. 4 times -3 equals -12, excuse me. All these are negatives. 8 times -1.5 equals -12. 24 times -0.5 equals -12. That's it. They are definitely inverse related. That's really horrible English, but you get the idea. That's all there is. Good luck. See you in math class.